Welcome to Lucky Section 13. We're on our way into sort of the belly of the beast today as it comes into mixture proportioning. I wanted to take a second to review a little bit about where we left off last class. Last class we were talking mainly about ACI 211, and we were saying that ACI 211 was really sort of the authority on mixture proportioning. And it's a series or a set of steps that we're going to use to try to figure out the volumes of the different materials that we're using in making concrete. And we said that the first step in the process, step one, was to gather information. So here we're going to assemble information, and that information is going to describe a few different types of things. So what types of things are we trying to assemble information on? All right, the properties of the aggregates or the properties of the materials. All right, so the properties of materials, and in addition, all right, exposure and requirements for things like strength. So those are the types of things we're going to be looking at. The second step in the process was to determine what? Slump or workability. Now, we will talk a little bit more, but slump is sort of an indirect measure of workability. And that's what we're going to be doing in the second step. And we're going to try to get an idea of how workable we can make the concrete so that it can be placed repeatably. The third step that we were talking about is related to determining the maximum size of the aggregate. And initially, this may seem like a relatively trivial step to pick out the largest aggregate size, but we learned that it wasn't so trivial because of why. Right? This is really going to dictate the paste. It dictates the paste volume, and this is going to control everything else that we're looking at. All right, all the other properties are going to really be related back to the paste volume. So step three, while it seems like a relatively simple choice, while it seems like a relatively simple selection or decision to make, it's really going to be an important decision that we make overall. Step four is the step that we're currently working on, and step four is to look really at water, and then secondarily we're going to start to look a little bit at air. And we said that we could bring the entire lecture down, really at least to start with, into one graph. And that graph we had water content plotted on the y-axis. On the x-axis we had slump. And then we had a series of lines that looked something like this. And we had a small aggregate and a large aggregate. And the basic idea was that we said that we could use this graph to explain a lot of the different aspects of this particular mixture proportion. We said as we went from a large aggregate to a smaller aggregate, we would expect the volume of the paste to increase because of the surface area, and that increase in the volume of paste would correspond with an increase in the overall water content. We said that as we move from the left to right on this diagram, as we increase the slump, that would correspond to an increase in paste as well. So we'd have an increase in paste, or we'd have an increase in the water content as we're trying to make the system more flowing. Now, the final thing that we got into discussions about was this idea of air. And we talked a little bit about the idea that we're going to have two types of air inside of our concrete. And we gave them the names. We had entrapped air, and then we had entrained air. And you'll remember that the entrapped air was really the air that was generated by the mixing process and sort of got stuck inside of the system. Tends to be a little bit larger in size, tends to be a little bit more irregular in size. The entrained air is the air that we are going to, quote unquote, add to the system. And when I say add here, what we're really doing is we are really putting in an admixture, a surfactant that is going to help us to stabilize air in the system. And that's what we're looking at. And this stabilized air is going to help us out because it's going to provide a pressure relief inside of the concrete. It's going to provide a way that we can relieve some of the pressure that starts to build up when the water starts to freeze and expand. It's going to delay the time it takes that concrete to saturate, and it's going to be something that we can look at in a beneficial fashion. Now, I left with probably the world's worst cliffhanger ever. It wasn't Who Shot JR, and it wasn't anything like you see on Fox where they're trying to get you to watch the show next week. I left you with the slide that we see in front of us. How much air are we going to have inside of our concrete? And we said that there are going to be 3 lines when we get into the tables in a couple seconds to start discussing this, and it depends a little bit on the exposure condition. On our y-axis, we've got the total air content, which we'll come back to a little bit. And on our x-axis, we've got the maximum size of the aggregate. Any idea why these graphs would depend upon the size of the aggregate? The paste volume. So as we increase the aggregate size, what's going to happen is the paste is going to decrease. And one of the most crucial things that we're going to discuss in this class is that while we do all of our measurements and we do all of our measurements in the field talking about the total volume of air, the air is not there to protect the total volume of the concrete. It is there to protect the paste. The air is there and it's only going to work on protecting the paste. So as we decrease the amount of paste in the system, as we move to a larger aggregate size, oh my goodness, mouse is wild today. As the paste increases, what's going to happen is, or as the aggregate size increases, the volume of the paste is going to decrease, and we can get away with using less air in the overall system. There's less paste there to protect. A good rule of thumb is we are going to need about 18% air by volume of the paste. So 18% by volume of the paste is what we're looking to have in terms of entrained air. Now you will notice that these numbers are much, much lower. These numbers represent the volume of air that's inside of the overall system, inside of the total system of our concrete. How much air depends upon the type of the structure. It's going to depend a little bit on the climatic conditions. In Florida, you wouldn't expect to have as much freezing and thawing as you may have in Indiana. You may have something very different in some other place. So a way that we are sort of going to take this into consideration is through this idea of the exposure conditions, where we're going to have mild exposure, where we may not have as much of a probability, let's say, of having a heavy saturation inside of the concrete and excessive freeze-thaw, all the way up to sort of the most severe cases that we could possibly have. The number of freeze-thaw cycles is going to start to become important in the whole discussion. The extent to which de-icers are used, because de-icers are going to start to change some of what's happening inside of our structure. We'll also look a little bit at the water-to-cement ratio. And the water-to-cement ratio is going to be related here for 2 main reasons. One is because the water-to-cement ratio is going to be incredibly important for the strength of the paste itself. And the second thing is the water-to-cement ratio is going to dictate the permeability of the paste. And as we change the permeability, what we're going to be changing is how fast the water is entering that concrete. So we're changing its likelihood to saturate. The more difficult we make for the water to get into the concrete, the more difficult it's going to be to saturate that concrete. Now here's a picture looking inside of our concrete at one of the, what I would say is probably one of the most fun tests. If anyone's never had the opportunity to do this, I'd be more than happy to set you up for a day. Looking through a microscope and trying to figure out how much air is inside of concrete. What we've done is we've taken a picture of this concrete and we have placed these lovely yellow grid lines on top of it. And what you would be doing with the microscope is you would be moving from one point to the next point, to the next point, to the next point, and you would be reporting back what you see at those individual points. So ASTM C457 is basically a test method that's set up where you're going to look through the microscope and you are going to have the sample on a moving table. And you are going to move the table to look at what's directly below a specific spot inside of the microscope at this point, at this point, at this point. You're going to work your way all across the entire sample. You're going to do this not 6 or 7 times. You're going to do this 1,200 to 1,400 times. It's a great way to spend an afternoon. All right? And you are going to keep track of how many times did you come in contact with paste? How many times did you come in contact with air? How many times did you come in contact with an aggregate? What you're going to do is you're going to basically be, by recording this 12 to 1,400 times, what you're going to be doing is getting a good statistical representation of the volume of air, the volume of paste, and the volume of aggregate inside of the system. And this is what the current standards for doing air measurements on hardened concrete are really based on. Now you may say, well, that sounds like a lot of fun to do this. It's really a lot of fun maybe the first sample you do. The second sample you can really speed the process up and become good at it. By about the third sample, I think you've pretty much maxed out on fun. And unless somebody starts putting something into the concrete just to sort of catch your eye, like they shrink down little tiny pictures of bugs or something like that and put them on the surface of the concrete, it can be a little bit monotonous. So there are people who are actually trying to develop ways that they can automate this test and get this information back much, much quicker. And one of the techniques that's out there is to actually use something like a flatbed scanner. And right now they're really struggling with how much resolution do you actually need, but there are groups who will coat the surface with different colored materials, use a flatbed scanner, and can get quite a lot of information and do image analysis to figure out things like the statistical distributions of the air inside of the concrete. Now, as I mentioned, when we start to entrain our air in our concrete, we are going to go to a slightly different table. So there's going to be 2 series of tables. There's going to be a series of tables for concrete that doesn't have air entrainment and concrete that does have air entrainment. So if you're looking at an air entrained concrete, you would now be coming into this table. This is exactly the same information that we saw in the previous graphs. You will notice that we've got the maximum size of the aggregate that's listed in the columns. In the rows, we have the slump that we're going to be using. And I believe last time we were talking about an 1.5 inch aggregate. We were talking about a 3 to 4 inch slump. And we saw last time that we would have about 290, I believe that was the 290 pounds per cubic yard that we were seeing for the amount of water that we would have. In this new table, you notice that we've got only 275 pounds per cubic yard. So we've reduced the amount of water. Does that make sense? Mike is shaking his head that it makes sense to him. Why can we reduce the amount of water when we're using an air entrainer? It's going to add to the workability, and all of a sudden now you have fluffy paste inside of the system. You've got air that's taking up some of the volume in between those aggregates. So before, you'll remember, we talked about paste being what needed to be in between the aggregates. And one of the real tricky questions is, when you start to discuss paste, is air part of the paste or is it not part of the paste? Well, it's not part of the aggregate system. It's not really part of the paste system either, but what it does is it gives you a little bit of extra space in the system, and it really provides this idea where you can all of a sudden get better flow or workability inside the material. So we can reduce the amount of water a little bit by placing some air inside of the concrete. You'll also notice that as we drop down to the lovely pink salmon colored part of the graph that I've highlighted, this tells you the recommended amount of air content for a given level of exposure. So if it's mild exposure, moderate exposure, severe exposure, it tells you the total volume of air that you should be targeting. So for our beam, and we'll see this in a couple of seconds, moderate exposure will tell us that it's about 4.5% air. This is the exact same information that we saw in this graph back here. The cliffhanger graph is exactly the same information. As I've listed at the bottom here, the total volume of concrete is what we're looking at here when we talk about these numbers, but in reality, we're really protecting the paste. We really want to have the air inside of the system. Now, the A student is going to look and they're going to ask the simple question, well, what's the difference between mild, moderate, and severe? I sort of understand it if I'm ordering a salsa at a nice restaurant, what mild, moderate, and severe are, but what do they mean when we're starting to talk about freezing and thawing? And I've pulled out these definitions just to give you a little bit of an idea. Mild exposure, the air is mainly in the system for workability. Frequently you will find air added into your concrete to save money. One of the things that we will notice is if we can reduce paste, we can save money inside of the system. Air can be cheaper than the water and cement that it replaces. You may say, well, water is not that expensive. Well, water might not be that expensive, but it's replacing cement. You'll also see, I believe you're going to start to see this used more and more as you start to see people discussing the amount of water that is embodied in different materials. When I was in Australia, I was somewhat amazed at the level of attention that they were paying towards sustainability aspects as it relates to the amount of water that's being consumed in producing different materials. And one of the things that you will recognize is when we put water into our concrete to take part in this reaction, that's water that we're not getting back to fill up swimming pools, to keep lakes maintained, and things like that. Now, while we may go outside and we may say that in the last few days water is not a scarce item, it's becoming more and more scarce, and people are worried about protecting watersheds, and they're worried about moving a lot of these, moving a lot of water out of particular regions. So this will become much more important. Can be used in indoor and outdoor concrete. Also, there'll be no exposure to de-icing chemicals. Moderate exposure, no direct application of de-icers, but they may be around. You may see something splashing up onto them. Freezing and thawing is expected, but it's a relatively nice freeze-thaw environment. Severe exposure is the worst condition. Right? This is going to be the pavement bridge deck. This is going to be the loading dock slab and outside of the building where they're dumping full bags of sand out there to keep people from slipping, and it's constantly covered in water. This is really the worst condition, the severe condition like you would expect. So as I mentioned, to the estimation for our example problem to estimate the mixing water and air content, we're looking at about 275 pounds per cubic yard for the water. We're looking at a moderate exposure, which tells us that we're targeting about 4.5 volume% air. Now, one of the things that we will point out, and this is outside of ACI 211, but what you can do at this point is you can make an adjustment for your water based on a whole lot of different items. Remember, ACI is just really sort of a guideline to help you to start to do mixture proportioning. What you're going to start to do at this point is you're going to say, well, our aggregates are very different than the aggregates that were used in order to make ACI 211. What you will find out is that the aggregates that we use in the state of Indiana are really close to what they used to make ACI 211, because a lot of that information came out of work that was done in Illinois, Chicago, Indiana. So our aggregates are a lot like their aggregates, so we don't have to make a lot of adjustment. But there'll be other places where the aggregates will be very different. You'll see people adjusting depending upon where the void content is occurring, how much sand they have in the system. People will adjust based on the quality of the sand. A rounded sand has less surface area. A natural sand or a crushed sand is going to have a little bit more surface area. You'll see people adjusting for the coarse aggregate shape. You'll see people making adjustments for supplemental materials, and then they'll be adjusting for chemical admixtures here. So typically you'll see people, you'll have a little bit more experience, and they'll say, well, every time I use ACI, I'm always a little bit over on water, so here I'm just going to save myself some time, short circuit the process, and I'm going to take some water out of the system right now. Again, the tables, if you want to have them so that you can actually use them for homework, here's a blank version, and then we've got the same version. It's just a little bit better because it's all in metric. No one seemed to like that it was better in metric. Step 5. This is the most artistic of the steps, because this is the one that really requires engineering judgment. This is the one that puts fear into the undergraduates' eyes, because they now all of a sudden have to think. Right? 331, somebody takes this class, and this is the one step that they're panicked on because they have to make a judgment. The rest of them are going to be straightforward, turn the handle, get my calculator fired up, and the answer will spit out, and everyone will get the same answer. Here you actually have to take a little bit of time, and you have to look at the water to cement ratio that you're choosing. And I will say that this is not an easy part of the process because there are a lot of things that need to be considered. Now I'm going to take a step back, and I'm going to point to some other civilizations, and I'm going to point to the Mayans. Anybody know anything about the Mayans? The Mayans are from Mexico. And the Mayans were fantastic builders. So here we can see, I believe this is Chichen Itza, but I would have to look. This is one of the Mayan cities. And one of the things that's really exciting about the Mayan cities is you will see that the Mayans were very, very excited about the water to cement ratio inside of their concrete. In fact, the Mayans had one of the gods that they were into was the water god named Chac. So he was one of the most worshipped gods in Mesoamerica. It turns out that Mayan society was based around sacred wells or cenotes, which were freshwater regions. And they were very excited about water because it was associated with life, because it was going to help them with staying hydrated in the very warm parts of Mexico, Guatemala, warm regions of the country. It was also going to help them in growing maize. So if we look a little bit at Chac, you can see here we've got the eyes of Chac. He's got some earrings. He's got some corn from the earrings, a mouth. And one of the things that's interesting is if you look at Chac, and Chac is on every building, every structure, the trunk of Chac is very, very critical because it basically is a determination of the water content that they have going on at the particular time. So Chac has two faces. He's got a face with the trunk pointing upward, which is asking the gods for water. And he's got a picture with the trunk pointing downward, which is, no thank you, we have too much. So I think all of us who've been walking around outside over the last couple days will realize that we are currently in this state over here. By midsummer, we'll be back over into this state over here where people will be talking a little bit about drought. But let's talk a little bit about water to cement ratio and how it's going to be determined. We have a balance that we need to really be considering. Everything that we're excited about on the construction site, all of our short-term properties, we would essentially, if everything else was equal, we would want as much water in the system as possible, within reason. So workability, finishability, pumpability, flowability, for all of these things, we would say the water content could be fairly high, and it makes all of those aspects of the concrete, makes everything over there a little bit easier. On the other hand, all of the long-term properties of concrete, whether it's strength, durability, shrinkage, volume, stability, want the water content to be a lot lower. We want to keep the water content as low as possible. We want to get a nice, fine, tight pore structure inside of the system. We want to minimize the amount of water. So we have this balancing act that we've really got to go through where we say, well, how do we get enough water so that we can make the people placing it happy, but not jeopardize the long-term properties? And this is really where we start to see compromises coming in, and we also see a lot of people coming up with different ways to reach these long-term requirements. So again, if we go back to some of the pictures that we were looking at early in the semester, we will recognize that this is an image taken with a scanning electron microscope. You'll remember as we look inside of the scanning electron microscope, we have different features that we can start to point out. We've got these large white features, which were the unhydrated cement. We've got the dark gray areas, the dense CSH, and then we've got these mushy areas, which are really the pore structure, and that's going to be, or the big pores that we're worried about. This entire thing makes up the pore system. But these really dark regions are the most porous of the regions. It's the ground mass portion of the overall microstructure. And this is really going to be dictated by our water to cement ratio. So as we get a higher and higher water to cement ratio, we're going to see a lot more capillary porosity developing inside of the overall system. Water to cement ratio is going to be one of the most key issues that we're going to keep coming back to when we talk about mechanical properties, strength, elastic modulus, fracture, when we talk about volumetric properties, thermal expansion, shrinkage, when we talk about durability properties, freezing and thawing, transport, those types of properties. Water to cement ratio is really the key issue because water to cement ratio is synonymous with porosity. All right, so we're remembering that everything is porous, we're remembering porosity is going to be related, and we're remembering that the strength is related to the volume of the pores over the total volume. And one of the things that I will point out when you look at this equation, because I got a question on this, and one of the things I will point out on this equation is you will notice that the x-axis goes backwards, so you actually need to take that into consideration when you use that equation. It goes starts out at a value of 1 and works its way back to 0, so it's actually 1 minus this entire thing. But we'll talk a little bit more about that later on when we start to deal with these materials. We saw the fact that when we started to put materials together, we had leftover porosity in the system. This leftover porosity was the capillary porosity that we had, and we saw plots that looked like this, where we said really where we want to be, the magical place is 0.42 water to cement ratio. If we go much, much higher, we're going to have a lot of leftover capillary space. If we go much, much lower, we're going to have a lot of leftover unhydrated cement. So these are all concepts that we've seen before. How is that related back to estimating the water to cement ratio? Well, to estimate the water to cement ratio, we are going to look at two main aspects. We're going to look at strength and we're going to look at durability. And what we want to try to do is we want to choose the water to cement ratio that is the most conservative. You want to choose the lowest water to cement ratio. That is going to dictate the design.
Would that automatically put us on the left-hand side of the balance beam then? Like where you're saying the people who work with it and then the people who want it for durability, strength, etc. Those were all on the left-hand side.
Right. Well, what I'm saying here, you've got sort of this balance between, it has to be placed, so you've got to have some water in the system. Right? So that's on one side of the balance beam. On the other side of the balance beam, you've got all the properties that it impacts. But all of those properties aren't impacted exactly the same. So, for example, one of the things that we're going to see is strength may tell us that the water to cement ratio of 0.6 is fine for what we need for strength. But for durability, we need a 0.4. What I'm saying here is the lower of those two water to cement ratios is really going to dictate what we need for the long-term performance. Because having a concrete that's adequate for strength but it falls apart after 2 years because of freezing and thawing, that's not really the solution that we're after. So we want to take the water to cement ratio that's the most conservative for our particular design. Now, as I mentioned, you'll see in some of the older versions of the code, the compressive strength is going to be related to the water to cement ratio. And again, you're going to have two different water to cement ratios here. You're going to have a water to cement ratio for the non-air entrained concrete and then a water to cement ratio for the air entrained concrete, because the air that's inside of the system is actually going to be a very specific type of porosity. The big difference between the entrained air porosity and the capillary voids, there are two big differences. And who wants to go out on a limb and tell me what those two big differences are? Well, the capillaries are filled with water, and the entrained air is filled with air. So one of them is hollow, empty. The other one is filled with water. And the other big thing that you would see, size may be a little bit different. Distribution may be a little different. Shape may be a little different. What's the shape of a capillary pore? Could be tortuous, could look like a monkey, could look like anything, right? Doesn't have a particular shape. What's the shape of... I got somebody confused. They're looking for the monkey inside of the concrete. All right. Don't disregard. It could have an irregular shape. Let's go back to irregular shape. It's not monkey shaped. I don't want to see that on an exam. So our capillaries are irregularly shaped because they're leftover space from when the irregular cement particles start hydrating. Our entrained air is what type of shape? It's going to be spherical. Right? So it's going to be a very well-defined shape inside of our system. Again, metric table. Now, we can take some of these basics off the same type of chart that we were looking at before. We could take this exact same information and we could start to plot it on a graph like we see in front of us here, where we've got a design strength here, and this is a compressive strength, required compressive strength, versus the water to cement ratio estimated just based solely on strength. If we look at these curves, what you'll see is, irrespective of the aggregate size, there are a few trends that start popping out. As we start to go to a lower water to cement ratio, right? As we start to move down on this y-axis, we go from a 0.85 to a 0.8 to a 0.6 to a 0.4 water to cement ratio. What you will notice is the strength goes up substantially. So if we go from a 0.7 water to cement ratio, we may have a 20 MPa compressor strength. If we go down to 0.4, we may get up to 40 MPa. As water to cement ratio decreases, right? As water to cement ratio decreases, we get a higher strength. Higher water to cement ratio, lower strength. As we decrease the size of the aggregate, we start to see that the strength goes up as well. But this is really a less substantial effect. It's more of a secondary effect. And it really has to do here with the idea that we have a more homogeneous system with a smaller aggregate. We don't have as much stress and strain concentration inside of the system. We don't have as much of a potential for cracking to be starting inside of the system. So this is the basic idea for strength. Strength is pretty easy, pretty straightforward. Now, question?
How low can you go with your water in order to keep increasing strength?
You can go pretty low. And I know that doesn't answer the question down to, I'd like it to be 0.1 or 0.2. But there are people who've actually sort of sprayed it with a mist, and then they try to squeeze the entire system together, and they can make concretes that are very strong. The big issue that you start to get into is you will notice, and I'm going to jump here, and I'm going to need to draw on the piece of paper. Oh, that was fantastic. So what we've got is, if you start to decrease your water to cement ratio and you start to plot the strength, we would expect a graph that looks something like this. Whereas we decrease the water to cement ratio, the strength goes up. We know that it's going to be related somewhat to the volume cubed, and we'll see some sort of a cubic function. What ends up happening is, if you were to actually test this in real life, so this is in theory. In real life, what you would typically see from most applications is you would see that it would go up. It would go up to a certain point, and then all of a sudden you would see that the strength would either flatten out or start to go down when you got to real low water to cement ratios. And this here isn't really an issue of the water to cement ratio. It's really more of an issue of the fact that you've got poor compaction. So what's happening here is you're getting voids inside of the system just because it wasn't pushed together. It wasn't pushed together tightly, so you got extra entrained or entrapped air inside of the system. Now, one of the things that people have done a lot of work with is they've tried to make super high strength concretes. They actually press these materials so that they can use mechanical energy to try to press them together and get to very, very low water to cement ratios that are incredibly strong. But most of the time there's a physical processing limit in the field that requires that you use a certain water to cement ratio, whether it's 0.25, 0.3, something in that range. It's going to be really dictated by how you're processing the material. Okay? Other questions on that? Other questions in general before we jump on into water to cement ratio and durability? Okay, so back to the slides. When we start to look at our maximum water to cement ratio, we've talked a little bit about how it's related to strength, but there are a couple other durability factors that we need to start to consider. And these will be mainly related to freezing and thawing, mainly related to corrosion, and mainly related to sulfate attack. And what you will see here is the water to cement ratio is going to be incredibly important depending upon the level of exposure, because water to cement ratio is going to determine how things move through the system. It's going to dictate the transport properties of our concrete. So what you will see is, much like we saw when we were talking about freezing and thawing with the different exposure classes, you'll see the sulfate exposure listed over here on the left-hand side of the table, where we'll go from something that may not have a lot of sulfate in the system to something that's a very severe sulfate case. You will see the water to cement ratio being specified, and one of the things that you will notice is as the case gets more severe, as the sulfates in the system become more severe, you're going to see that the water to cement ratio is going to drop down. The maximum water to cement ratio that's permitted is going to drop down. You're going to see it in the 0.5 range. It's going to drop down into the 0.45 range, and the 0.45 range is significant because this is where we start squeezing out the capillary pores, 0.42, 0.45 in that range. And then we're going to drop down to 0.4, where it makes it very difficult for things to be transmitted through the system. Now that severity, instead of just kind of like an American bandstand number like we saw with freezing and thawing, where I think it's kind of bad, I think it's, it's less bad than it was good. It's a 7. I could dance to it, whatever we were using to determine those exposure conditions. Here with the sulfates, you're going to see that they're a little bit better quantified, where they're talking about the sulfate in the soil or the sulfate in water that it's exposed to, and you're going to actually use numbers to make some of those decisions. You'll also see that they will list a limiting or a minimum compressive strength as well. So you'll have a water to cement ratio requirement that needs to be met, as well as a compressive strength. You'll also see that there'll be a little bit of a discussion here where we may want to start to use different types of cement, and this is because it's going to alter the chemistry, and we're going to get a cement that is less reactive with the sulfate that may be inside of the soil. Different exposure conditions. Here we're looking at corrosion, and we're looking at freezing and thawing. So much like we saw before, if we don't have any freezing and thawing, there's no de-icers, there's no aggressive substances, then we really don't worry about the water to cement ratio as it's related to durability. We allow strength and workability to be the only thing that we're going to consider. And we choose the strength based on our structural requirements. If we need a concrete that we start to worry about the permeability, we're going to start to specify a 0.5. Freezing and thawing conditions, we'll get down to a 0.45, and we'll get down to something for chlorides that may be even a little bit lower. Now, I'm going to use this graph because I think that this is, and we'll see this graph coming back at the end of the lecture, where we start to talk about a graphical method to look at mixture proportioning. This is a graph from some of Ken Hover's work, and what Ken has done is he's tried to put all this stuff together onto one graph that you can start to use. So he's got the compressive strength listed on the y-axis, and he's got the water to cement ratio listed across the x-axis. The permeability coefficient is listed on the second y-axis. And what you will notice is, much like we saw in the graphs that we were drawing, we've got the line for the non-air entrained concrete. Water to cement ratio goes down, the strength goes up. We see that that line shifts for the air entrained concrete because we have porosity in the system. So again, that line makes reasonable sense to us. And then what we can see is there is another line that starts to come onto this graph, and this is the permeability. This is our coefficient of permeability. And one of the things that you will notice is the permeability changes dramatically with our water to cement ratio. The permeability is very much dictated by the amount of capillary porosity in the system. And you'll notice that when we get down to our 0.45 and our 0.4, we end up with a very, very low coefficient of permeability. On this graph, he's related the permeability back to our water to cement ratio, but also started to talk about some of these requirements we saw before, where we might have a 0.4 water to cement ratio for corrosion protection, or a 0.45 if we're worried about moist freezing. So the idea behind this graph is, all of a sudden you can look pretty quickly and remember all of the main points that you need to be considering. You want to choose the most conservative water to cement ratio for strength, freezing and thawing, sulfate attack, and corrosion protection. Questions or concerns before we jump into a slightly different topic? We start to talk a little bit about statistics. Everybody's favorite topic, statistics. Nobody's favorite topic? Second favorite? Okay. All right. Statistics. How is this at all related back to the design of concrete? Well, engineers love to do things based on averages. Averages are fantastic for engineers. We want to be average. We want to make sure that everybody is average because that's a good thing. If you are a concrete producer who designs your concrete based on the average strength, that means half of the time you're designing something that has sufficient strength, and half of the time you would be designing something that is under strength. So we don't design based on the average. What we're going to do is we're going to design based on some sort of a lower limit type of analysis. Now, we're not going to ensure that 100% of what's made is above this average, because statistically that doesn't make a whole lot of sense. But what we want to do is we want to actually start to try to design our materials, or we want a different target strength than the required strength that we would have in our particular structure. So if we say that we're required to have the strength that's dictated here by the red dashed line, we want to target a strength that's slightly higher so that our average is higher, so that the majority of data falls above that required minimum strength. And the way that we start to do that when we start to look at our concrete design is we're going to start to define a few different numbers. We have the specified compressive strength, which is shown here as this red dashed line, and we have the required compressive strength, which makes sure that we're above that, and it's going to be above by a certain number, X standard deviations. So we've got our required compressive strength, and then we've got our specified compressive strength. So our specified compressive strength, our required compressive strength, which is going to be slightly higher. Now, there are a few simple rules that we can jump into here. Our specified compressive strength shouldn't be less than 2,500 psi, should be based on the tests of compression cylinders, should be based on a 28-day strength unless noted otherwise. Right, these are just some of our general rules that we're looking at for our mixture proportioning. And in general, our required compressive strength is always going to be slightly higher. It's going to be somewhere around 500, 600, 700 psi higher, but it's going to be based on a series of rules. So again, we've got a series of rules of what that required compressive strength should be. Now, the simplest rule that's out there is this particular table. And if you want to just do the simple rule all the time, you would just pop it open to this table, 5.3.2.2, and you would be all set and ready to go. This is the table you use if you know nothing about the production at your facility. You've never made concrete before, you just bought a truck, you're ready to go to town, you're ready to start making concrete. This is the one that you're ready to go ahead with. You would also use this if you haven't made concrete, or you haven't made a similar concrete to this, and similar means within about 1,000 psi of compressive strength. So if your concrete, the specified compressive strength, is less than 3,000 psi, you're going to add 1,000 psi to it. Between 3,000 and 5,000, you're going to add 1,200 to it. Greater than 5,000 psi, 1.1 times F prime C plus 700. Simple rules of thumb. These give you that margin of safety, that factor of safety that we were talking about. Now, unfortunately, these are, since they're so simple and easy to use, these are going to be, any guesses? How conservative do you think these are? Very conservative. Very, 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 very conservative. So what a lot of people want to do is they want to start to say, well, it's not like I've never made concrete before. I mean, we send out 500 trucks of concrete a day. We've got a general idea of what our quality control is. If you have some idea of what your field strength may be at a particular facility, you can start to use this correction table. And what this correction table does is it takes the number of tests that you're going to perform, or the number of test data that you have, and it allows you to start to modify the standard deviation that you have from those particular test data. So if you have a lot of data, you can simply use the standard deviation directly. If you have less and less data, you're going to multiply that standard deviation by a factor that is going to make sure that you're conservative. If you're less than 15 previous tests, go back to the tests that assume that you've never made concrete before. Most conservative of everything. And when you do that, you're going to start to account for the deviations in strength. using the records from your facility. And now you've got a few different rules where you're going to be able to say my required compressor strength is going to be determined from these two equations down here. I'm going to go through and I'm going to say it's the compressor strength plus 1.34 times the standard deviation. It's my required strength plus the compressor strength plus 2.33 times the standard deviation minus 500. I'm going to use the larger of those two values, and I'm going to use that as my required compressor strength. Greater than 5,000 psi, we're going to move to a slightly different equation, and we're going to start to use this. Again, you use the larger of those two values to target your required compressor strength. Now, a few things that we'll talk about when we start to talk about the idea of testing. A test, when we talk about compression, is the average of two cylinders. So you take two cylinders, you average them together, that is one test. Any 3 consecutive tests must equal or exceed F prime C. Now, this rule is in there to make sure that you are not trending in a bad direction. All right? It's to make sure that you're producing something that's relatively consistent. Make sure that you're not heading in the downward slope. Because what you don't want to do is you don't want to find out that, a good example of this is your team's favorite quarterback. They can have one bad game. They maybe get away with 2 bad games, but you're not going to let them have 8 bad games in a row because in the 1980s they were a great quarterback. All right. All of a sudden, if they run off a series of 6 or 7 bad games, you can say, hey, there's something amiss here. So what you want to do is you want to make sure that any 3 consecutives must equal or exceed F prime C when they're averaged together, and this makes sure that you're maintaining sort of the minimum acceptable quality. No individual test, this is the average of 2 cylinders, is going to fall below more than 500 psi below F prime C, or 0.1 F prime C if it's greater than 5,000 psi. And the other thing that I will point out is all your field cured concretes need to be within about 85% of the laboratory concretes. Your laboratory concretes, you will always get, well, I shouldn't say always, you will almost always get better performance from the laboratory concretes because they're kept at a more constant temperature, they're kept in a gentler environment, they tend not to dry out as much or get kicked around or get run over by a truck or other things like that that can happen on site. Okay, so you want to make sure that you're really making sure that your field cured concretes are really representative of what you're getting in the lab. So accounting for these standard deviations, this should have been a magic yellow slide. We assumed here that there was no field data. This is the example. We said that we had to have 3,500 psi. We're going to add 1,200 to it because we're in this range. So we're going to design our concrete beam for 4,700 psi as our required compressive strength. So we would now come into step 5. We would select our water to cement ratio. 4,700 is between 4,000 and 5,000. We would interpolate between these two values and get 0.424 as our water to cement ratio based on strength. We would go back. We would look at our water to cement ratio based on our exposure conditions. And I believe, I don't remember exactly, but I believe that we had no exposure conditions that we needed to account for, or they were moderate exposure conditions, so none of these would apply, and we can start to move forward. Okay. So up to this point now, we've looked at some of the basics, and I want to wrap up here, and then we'll start off the next lecture talking about chemical admixtures and how things can change. So just a little bit in review. We went through, we assembled information, we got our slump that told us a little bit about the workability of concrete, how it was going to be placed. We talked about the maximum size of our aggregate because that was going to dictate the amount of paste that was in the system, so that was an important choice. We then went in and we started to try to figure out the overall water content and our water to cement ratio that we were going to have in our particular mixture. We said that we want to choose the most conservative water to cement ratio when we consider strength and durability, and durability here is going to comprise sulfate attack, corrosion, and freezing and thawing. So the most conservative of all those things. Any questions on this? Otherwise, we will start off lecture 14 looking at chemical admixtures. Question?
Yeah, you had mentioned corrosion control for for your water cement ratio determining.
Right.
Can you elaborate a little bit more on that? Why there is at least a maximum for your water to cement ratio?
Okay.